Very exciting times, people. We are back to Eigenstuff. So we're going to first list a bunch of things that are very helpful for playing around with eigenvalues and eigenvectors. Sneaky monk tricks. A list of sneaky monk tricks here. So, and then we will get to diagonalization, which is a beautiful thing. There are a number of elegant things we have to think about there. Wow. But, and that will take us through to we'll be fairly well through the course by then. There's really just some extra stuff that will lead us into singular value decomposition. So, great. All right, but let's focus on eigenvalues and eigenvectors. So it's all about this equation. As we've seen, we've had this diversion to think about determinants, right? Because that's the best, generally speaking, the best way for us to find eigenvalues, at least analytically. Okay. There are numerical things. Fine. All right, so the game was that, and so let me just focus here, right? So it's just two pages in this little piece here. So we find the lambdas by solving this equation, right? Which is the characteristic equation for A. So it's A minus lambda times the identity. Take the determinant and set it equal to 0. So right, we find the roots of that. There are always n roots. A is n by n. So let's get that in there. Right, this is n by n. Of course, this is n by 1. This is just a scalar. Right, it's a number. And this is n by 1. All right, and then, so once we've done that, once we've got each lambda, we go and solve a null space equation, which we think is great, right? We love that. It's good. This is originally set up, right? So, oops. We solve this equation. Let me highlight those two pieces. Yeah, we solve this equation for each lambda. As we've seen, we can get into trouble if lambdas are repeated because we may not have enough dimensions in our associated eigenspace. All right, so we've had this example before. We'll keep going with it. Right? It's a very simple little matrix. It's symmetric, which is a symmetry will matter, will be meaningful. This is for later. Okay, very interesting thing. We'll get to it. So from this matrix, we end up with these two eigenvalues, 3 halves. Importantly, this was greater than 1, and this is smaller than 1. So there's sort of an expansion in one direction. Yes, good. So there's an expansion in this direction here, 1, 1, and a contraction in that direction. All right, so we've got through this. Good. So that's going to be our example again. So, and we'll just do a few little calculations for it. Okay, so first thing is that the determinant of A is equal to the product of the eigenvalues. So that's probably a little surprising. Yeah, so it's on the next thing. Okay, so stop zooming. So let's get this right. So the determinant of A is equal to the product of the eigenvalues, right? No plus or minus. We had before that it's equal to plus or minus the product of the pivots. So this gives us a connection to the pivots. Okay, so let's look at our little example. So the determinant for A is 1 times 1, right? So it's this piece minus this piece here. This product minus a half, it's a half. So that's 3/4. And the eigenvalues multiplied together, it's 3 halves times a half equals 3/4. So that's no way of proof, of course. They checks out. So why is that? Here's the general, right? So here's the general characteristic equation for an n by n. The excitement is just building here. It's a whole slew of these little SMTs, sneaky monk tricks. So in general, it's some nth order polynomial. There are minus lambdas in it, so it's better to write them like this, right? So here's a minus lambda. This is some number, of course, lambda 1, whatever it is, right? Lambda 2. So here's our example for the current, for our little 2 by 2. right? Now, you can just take this equation and set lambda equal to 0. Of course, we want this thing to be equal to 0, but this is just a polynomial. We can set lambda equal to 0. So that would get rid of this piece. All of these lambdas are 0. I'll use a different color. Right, so we're going to set lambda equal to 0. So that this would vanish, this would vanish, this would vanish, this would vanish. And you see you're left with this result, that it's the product of the eigenvalues here. Lambda I equals 1 to n. Cool, right? Awesome. And from before, we also have, and it depends on the number of row swaps, the determinant of A is equal to plus or minus, I've written the wrong thing. I want a product here and here. Product, I'm thinking about traces, pivots. Okay. Big pi for P. All right, good. Traces are next. This is where we're getting myself into trouble. So traces are next. So trace is a trace of A. So we say the trace of A, and then we write it as TR, little capital T, little r. It's a sum of A's main diagonal elements, right? So we're only talking about square matrices. Again, this section is all about square matrices, determinants, eigenvalues, and so on. So it's the sum down the main diagonal, right? Just sum them up. Okay. Trace of A, it's a sum of A's. Right, I think that's worth looking after. Okay, so our example, very simple thing. So the trace of 1, a half, 1 is just 1 plus 1 equals 2. And the sum of the eigenvalues for this example, right, is 3 halves plus a half equals 2. So that seems a little magical, so we'll quickly, right, these are odd connections, very nice things. Right, same thing. So here's a general 2 by 2, so we could expand this, and this actually gives us a couple of things. Some trees are meeting their match outside. So the determinant, right, we have this formula. This is a general 2 by 2 minus b times c. So let's expand this out. We see we get a lambda squared. There'll be minus a plus d times lambda. And maybe, it's probably I should do it. So let's put a plus here. And I'll just keep the minus lambda. I'll do something a little, I think this is good. Minus lambda squared. And then I want a minus lambda here. Plus AD minus BC. Right, so let's just highlight the parts of the polynomial, the rest are constants. We've got this, and over here, of course, once we work out the polynomial, we'll have these two roots, right? Here they are. So if we expand this one, we get minus lambda squared plus lambda 1 plus lambda 2 times minus lambda, and then plus lambda 1, lambda 2. Right, so the variable is here, and the rest are constants. So matching things up, we actually get both of the results we've had before, right? So that should be a plus there, right? So matching these two, right? These things are equal, yes? So we get the two results we've already had. So lambda 1 plus lambda 2 equals A plus D, which is the trace of A, and AD minus BC equals, well, I should write it the other way. Lambda 1 times lambda 2, right, this piece here, is equal to this piece here, equals, right, just the constant term, AD minus BC, which is the determinant of A. Right, so for both of our results we've just shown, this is just a little argument for a general 2 by 2. Now, of course, that's not enough. We have demonstrated how this one works, right? So let's argue a little bit, just quickly. which we'll do for many of these things. So if we had a general n by n, we've got the determinant of the characteristic equation, expand it all out. This thing, if we think about it, we're going to have a term which is minus lambda. If we think about the big formula, lots of ways to think about this. There'll be a minus lambda to the power of n, right? So that's going to be picked up when all of the diagonal elements are multiplied together. Think about the cofactor method. And at the same time, right, we'll be able to, right, there's going to be the main diagonal elements minus lambda, so A11 minus lambda, A22 minus lambda, A33 minus lambda. Those things are actually all multiplied together at some point, and the only way to get all of the powers of lambda to the end is from that product, and the only way to get lambda to the power of n minus 1 is also by choosing n minus 1 of those lambdas, and then the A11 or the A22 or the A33. So think about it a little bit. And when you put all of those together, there are n of them, and sitting attached to each minus lambda to the power of n minus 1 is an A11, an A22, A33, and they all add up to give us the trace of A. On the other hand, if you expand this piece out, this is easier to see. There'll be minus lambda to the power of n, minus lambda to the power of n minus 1, and then you pick up the sum of the eigenvalues. So those things are the same. Okay. So this is something you can always think about that a little bit, but it's a result that we need to know, or you should know. You can always check this, right? So so we can always check this. If you figure out the eigenvalues for a matrix, it's a simple little check. Same with the determinant, right? So the product of the eigenvalues should be the determinant, just to make sure you're doing the right thing. Okay, so I've alluded to this before, so we'll call it a sneaky trick. So this is a recapitulation of some of the things we've had already. Okay, so that's good. And I'm really just going to lay these out. These have been these things we've seen in assignments or in previous lectures, just being documented here. So yes, the determinant is the product of the pivots with a plus or minus depending on row swaps. Depends on row swaps. Required to uncover U. And there's no plus or minus here for the eigenvalues. Good. So this is true. So we have a sequence of these sorts of things. So if A times V, right? So if V is an eigenvector of A with eigenvalue lambda, then V is also an eigenvector of A to the power of n with eigenvalue lambda to the n. So you just repeatedly try this, right? So you do A to the n times V equals A to the n minus 1 times A times V. Just break it off. We have this result. So the lambda can come out the front. Now we have A to the n minus 1 times V. And then you just keep doing that, and we'll get a lambda each time until we get back to V. Easy. The next one, if we take A and we add something times the identity to it, then we have all the eigenvectors will stay the same and we'll shift, right? There's a shift. It's a shift in the eigenvalue. So again, you can approach this in different ways, but it's not too hard to just figure this out. So we can break this into two pieces. It's A times V plus T times the identity times V. Well, let me do it. So then this is lambda times V. This is the one thing we know. Identity times V is just T times V. So then we can pull them apart. We'll put them back together. So we have blob times V equals number times V. So therefore, the number is the eigenvalue of the blob, and the V is the eigenvector. Okay. Last one in this little sequence. It actually follows from Sneaky Trick 5. 4, I should say. Matches Sneaky Monk Trick 4. for, let's say, n. You know what? I don't want to put an n. I'm going to fix that up. It's bad. K equals -1. I'm going to go back here and fix this up. Because n is the dimension of the matrix A. K, 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 that's a K, and that's a K. Good. Better. Right, A is n by n. Let's put that in. Just generally speaking, we use that all the time. So good, good, good. So we can do this one. We could just put -1 in, but I'm going to quickly derive it. So if a to the -1 exists, then we can just pre-multiply both sides by a to the -1. Lambda is a constant, just comes out. So this is the identity. We'll switch them around and divide both sides by lambda. We get the result. Put this here, put this one here. Yep. It's great. It's great. Sneaky monk trick number 7. Good. Good. So this is a big deal. So if A's eigenvalues are different from each other, then A's eigenvectors form a basis for Rn. They're linearly independent and they form a basis for Rn. Right? So no two eigenvalues match. There's going to be a very surprising thing if we add symmetry to the matrix later. So there are a couple ways to think about this. We can assume, put this here. Yep. This is a cool thing. So let's work through it. So I want to color it differently. Okay, so let's just think about this. So every pair of eigenvalues they're different, right? So they're all the roots to the characteristic equation are distinct. No repeated eigenvalues. Then then the eigenvectors form a basis, which is incredibly important, right? Because it means that the matrix has a nice basis for Rn. We can do good things with it. Diagonalization is where we're going to get to with that. So this has to be true. If they're dependent, this has to be true for some C1, C2 not equal to 0. Right? It's our null space equation. So we can play with this a little bit. So we could do 1. Let's multiply both sides by A, pre-multiply. V2, and that equals A times 0. Right, so this is equal to 0, of course. And then A times V1, so we're going to have lambda 1 times V1 plus, right, so we're going to use the fact, let me move that, okay. All right, so that's true, so that we have that. Let's call it 1. We could take the original one, so we're pre-multiplying by A. We could alternately do something like this. We could say, just take this and multiply it by, so take all of this, and multiply by lambda 2. Lambda 2 times C1, V1, I'll try to make it readable, equals lambda 2 times 0. Right, we're just doing the same thing to both sides of the equation. So that would give us C1 lambda 2 V1 plus C2 lambda 2 times V2 equals 0. So let's call this equation 3 and 4. I'll do something different. I'll call that 1. Okay, so we'll call this A and B, and then we'll call this equation 1 and 2. So we can subtract, so 2 minus 1, we're going to subtract, right, this equation here from this equation. From the second one, yeah, good, good. Yep. And so these two pieces cancel, they're the same. And we end up with C1, and then we get this difference here, lambda 2 minus lambda 1 times V1 equals 0. And the only way this is true, right? V1 is not equal to 0. C1 is not equal to 0. So it implies that lambda 1 must equal lambda 2. And you can kind of, the idea is to sort of build up from here. So this is just a sort of a sketch to give you an idea of it. Should come up with a better proof of it. Okay. Build up from here for n by n's. So, but just to say again, very important result. If the eigenvalues are all different from each other, then we have a full basis generated by the eigenvectors of A. This last piece here is, or this on this page, number 8, is to say that, you know, sometimes things work out, right, very easily. So the inverse of AB is B inverse A inverse. The transpose of AB is B transpose A transpose. We can do some nice things with products, but this is not have I written this in a bit of a funny way? Yeah, I think I have. Yeah, this is not right. So this is eigenvalues and eigenvectors of A and B are not simply, that's what it should be, related to those of AB and A plus B, right? So a couple of things. So for example, so if AB share an eigenvector V and they have some eigenvalues, then we could just add them together and their eigenvalues would add together. Okay. And this would actually be true. A times B, right? We just multiply them and the eigenvalues would be products of each other. But this is generally not the case, right? So this is, you can't sort of glue them together if they're different or anything, right? So usually they are somewhat special. Okay, so that is, that's just a little grab bag of sneaky monk tricks, things to know about eigenvalues and eigenvectors. Lots of pleasurable pieces. We've proved them for arbitrary large matrices, generally speaking. Good. So the next thing will be about powers of, getting back to powers of matrices and this thing called diagonalization.